containing only carbon in their aromatic nucleus. Then we have the heterocyclics. So here, the carbocyclic group have one or more of another atom replacing carbon. And like I said, the other atom could be nitrogen, sulfur, selenium, silicon, nitrogen, and then what have you. These are the common hetero atoms that can replace any of the carbons in there. Now, a heterocyclic ring may comprise of 3 or more atoms, whilst the carbocyclic is just only one atom, which is usually carbon. The heterocyclic can have 2, 3, or more different atoms. They may be saturated or unsaturated. They may be saturated or unsaturated. So over here, if you can see my screen, then you could see that there are examples here. This one is an epoxide, okay, 3 atoms ring system with only one heteroatom, and it is saturated. It's saturated in the sense that all the carbons here are at sp3. Then we have this one, it contains 2 different heteroatoms, oxygen and nitrogen. Okay, it's also saturated. It doesn't have a double bond in like the first one. Then these other 2 down here are unsaturated. Unsaturated because they have the double bonds in there, meaning the carbon atoms are all sp2 hybridized. So this one is 5 carbon ring system with only one heteroatom, oxygen. Here, 2 nitrogen atoms. Okay. So when you see a heteroatom, a heterocyclic compound, beyond carbon, you are likely to see another atom in the ring. It could be nitrogen, oxygen, sulfur, or what have you. So try the following. Draw a 6-atom saturated ring system with only one heteroatom. You can do that. Draw a 4-atom unsaturated ring system with 2 dissimilar heteroatoms. I think you can also do that. Good. Now, how does these heterocyclic compounds occur? Their occurrence, where they are found, and their uses. So they are found widely in nature, and we can also synthesize them as well. They are found widely in nature, and we can also synthesize them as well. These heterocyclic compounds are essential to life. In fact, with time, some of the examples that will be giving you realize that most of the drugs, most of the medicinal compounds, and that we rely on for a lot of health issues, they are heterocyclic in nature. These heterocyclic rings or compounds constitute more than half of all organic compounds. Wow. This statement should tell you something. We always say that we have billions of organic compounds, billions, from alkanes to alcohols to aldehydes to ketones to carboxylic acids to all the ones that you have been exposed to as far as this course is concerned. If we are taking in terms of composition, then the heterocyclic group, they form more than half of all the compounds that exist. Alkaloids are heterocyclic, antibiotics are heterocyclic, amino acids are all heterocyclic, the vitamins, hemoglobin, and the hormones. These very essential organic compounds, in one way or the other, are all heterocyclic aromatic compounds. How do we name them? How do we name them? So I think after I saw this particular slide, I have shared other 2 slides with you. And those 2 slides, please, the reason why I added them was that when it comes to the nomenclature system, those ones are detailed. they've given enough information on different types of what heterocyclic system and how they are named. So whatever is captured here, always refer to that other slides to get more insight and more information there is. So they have their common names, and there isn't that kind of any known specific systematic name. But then depending on the type of heterocyclic, we have numbering systems, like we saw the numbering system in naphthalene, anthracene, and phenanthrene. Over here too, there's a numbering system. Now, the numbering system always starts from the heteroatom. So in the aromatic nucleus, the heteroatom that is found in the ring, that's where you always number from. In this case, see, we're numbering from the oxygen, the first one, and then you go clockwise or anti-clockwise. If there's a substituent, then that will guide you as to whether you should go clockwise or anti-clockwise to give it the least number. So 1, 2, 3, 4, 5. This is a furan. This is tyrphene. This is pyro. The difference is that all of them, though they are unsaturated heterocyclic compounds, the furan, the heteroatom is oxygen. The tyrphene, the heteroatom is sulfur. Then the pyro, the heteroatom is what? Nitrogen. Now, if you increase or if you substitute any other group, then you number so that you get to know the position of those substituents. So any other group that is outside the aromatic nucleus is considered a substituent. So this methyl group here is a substituent. And if you are to number from the nitrogen, you wouldn't want to go clockwise. If you go clockwise, it will be 1, 2, 3, 4, 5. The meter will be 5. But if you go anti-clockwise, it's 1, 2. And IUPAC always go for the least position for substituent. So then you go to have 2-meter pyro. At this stage, I will advise that get to know the common names of all these heteroatoms because they form their parent name. Furan is furan. Tyrphene is tyrphene. Pyro is pyro. So if I put any other substituent on it, it's just about you identifying the substituent name and then you add that parent name to it. So the last one here already is what? Tyrphene, because of the sulfur. Then you number anti-clockwise so that the chlorine will be 2, the bromine will be 3. Now these two are inorganic substituents, so you have to arrange them in alphabetical order. So bromo comes before chloro. So 3 bromo, 2 chlorotyrphene. That is how we name this or some of these heterocyclic compounds. It is not always that we will give you the structure to name. Sometimes we will give you the name to draw the structure. So please kindly let us try our hands on these 2 questions. First, draw the structure for the following: 2,3 diameter furan, 3 chloro, 2 meter tyrphene. Let's try our hands. Then the second one is name the following. So that one, we've given you 3 compounds and they are all substituted. And so we need to name them. So please, I'm giving you some 5 minutes. First, the question 1 is draw the structures. And the question 2 is name these compounds. Let's try our hands on it. And then I'll get back to you pretty soon.
Okay, Doc. Okay.
Please, are we done?
Yes, Doc.
Yes.
Okay, so for the structures, I don't know if any one of you can show his or hers, but then the naming, you can also call out what you got, and then we check whether it is correct. Then we move on. It's from Paul.
Yes, Doc. Thank you, Doc. Doc, I'm dealing with the naming first. The first one, A. 3-bromo, 4-hydroxy, fulan.
Come again.
It's 3-bromo, 4-hydroxy, fulan.
How did you get 3 and then the 4?
It's 4-bromo, 5-hydroxy, fulan, rather. Therefore, I start counting from where the oxygen atom is. So
And then you went anti-clockwise.
Yeah, then I went anti-clockwise. So it will be.
But then if you went anti-clockwise, you are getting 4-bromo, 5-hydroxy. If I go clockwise, I'm getting 3-bromo, 2-hydroxy. In which of them am I giving the least numbering to the substituent? 4, 5, and then 2, 3. How we get it?
Yeah.
So the name should be 3-bromo, 2-hydroxy, furan. That would be more appropriate. Yes, can we take the second one?
Hello,
Yes.
Doc.
Francis.
Doc, the second one, I got 3-ethyl 5-meter arrow.
3-ethyl 5-meter pyro. That is, you also went anti-clockwise in your numbering. If I go clockwise, I'm going to get 4-ethyl 2-meter. 4-ethyl 2-meter pyro. Now 4-2 and then 3-5. Which one is giving you the least numbering?
The 2-4-2.
The 2-4. So please always don't look at only one direction of numbering from the heteroatom, but look at the other direction too and check the one that is giving you the least numbering. Please, I hope that's okay.
Yeah.
Okay.
Yeah.
All right. Can somebody pick the third one?
Hello, Doc. 2
Yes.
2-ethyl 5-meter theophane.
Yes, 2-ethyl 5-meter tyrosine is correct. Because
okay.
whichever direction you go, you get 2-5. Okay. But then because the ethyl will be named first, that one is giving the least number.
Yeah.
Good. So you need to be trying your hands on more of this because that's how I'll be examining you. So take note of the questions that comes in. Now we have talked about these basic aromatic compounds: furan, typhine, and pyrrole. If we say they are aromatic, then we need to justify their aromaticity, isn't it? We know of benzene, and we'll be able to justify why benzene is aromatic, anti-aromatic, how it's done, non-aromatic, and all those things. So if furan, pyrrole, typhine are aromatic, then we need to know. And this information here helps a lot. So they all donate 2 electrons to the ring. Okay. You could see that if you look at their ring, there are 2 double bonds in them. So you might be tempted to say that then they don't obey the Haeckel's rule because the 2 pi bonds translate to 4 pi electrons. And we know the Haeckel's rule, the total number of pi electrons should be what? 2, 6, 10, 14, 18. So you might be tempted to think that these ones, they don't obey Haeckel's rule. But we are saying that the heteroatoms themselves have lone pair of electrons. Oxygen has 2 lone pairs, nitrogen has 1, sulfur has 2. So they normally donate 2 electrons to the ring to form part of the high electron system. So if there are 2 double bonds in there having 4 electrons, then one of the 2 electrons here will be added to make it 6. And that will make it what? Satisfy the Haeckel's rule. I hope that is clear.
Yes, Doc.
Doc, please come again.
Please, Doc. Yeah.
So what I'm saying is that aromaticity of furan, pyro, and typhene, okay? If you want to determine that they are aromatic, then first you have to check, are they ring? Yes, they are ring. They are cyclic, isn't it? Are they planar or flat? Yes, they are. Are they fully conjugated? Okay. Yes, they are, because you can see that you have a double bond, single bond, double bond, single bond, okay? And then the 2 lone pair of electrons on the heteroatom can be pushed into the ring to also be part of the pi electron system. And then when it comes to the Haeckel's rule, where we normally say there are 4n plus 2 pi electrons, we normally count the total number of pi electrons. Benzene has what? 6. And 6 forms part of the series of the Haeckel series, 2, 6, 10. So we are saying that if you take the first one, furan, how many double bonds are here? 2. These 2 pi bonds. Each one contains 2 electrons. So the total number of pi electrons is 4 here. Now, you might be tempted to say that, oh, if there are 4 pi electrons, then they don't meet the Haeckel's rule. And I'm saying that for furan, pyro, and typhene, they always donate 2 electrons from the heteroatom to the ring to be part of the electron pi system. So if these 2 electrons, one of them is donated to the ring, then it makes the total pi electron here to be what? 6 instead of 4. The same way this nitrogen also will donate these 2 electrons to the ring. Sulfur has 2 of the lone pairs. It will donate one of them to the ring. When they do so, then the total number of pi electrons then satisfy Haeckel's rule. And so we can say they are what? Aromatic, because then they obey all the 4 criteria.
Hello, Doc.
Yes.
My question is, the heteroatom, if you have that lone pairs, like the oxygen, which has 2 lone pairs, it is only 1 lone pair that it donates.
Yes.
To
The
make
other
it-
one, the other one does not form part of the ring. It only donates 1.
It only donates 1.
Yes.
So that it satisfies the Haeckel's rule and make it
Yes.
6.
So when you are calculating for the total number of pi electrons, if there are 2 lone pairs, you don't add all the 2. It is only 1 a lone pair. It's only 2 electrons that it is always ready to donate.
Okay. Thank you.
Any other question?
So like, Doc, so the third one, that one.
Hello, Doc.
It has the nitrogen. The nitrogen has the 2. If we can go back to the previous slide, Doc, please. The anhydrine, that is like the amino, the nitrogen, the second one, the pyro.
Yeah, the pyro.
Yeah, it has just 1 lone pair electron. So that lone pair is the one that is going to donate to form to satisfy the Haeckel's rule and make the 4 or the 6 pi bonds, right?
Yeah.
Okay, thank you, Doc.
All right.
Hello, Doc.
Now, in terms of resonance,
Hello, Doc. Hello.
yes.
Hello, Doc.
Yeah.
Can there be a situation whereby the furan, the pyron, and the typhene, there will be no lone pair? In that manner, how are they going to satisfy the Haeckel's rule?
So furan is furan, typhine is typhine, pyro is pyro. The structures that are given, and they are satisfying the Hackles rule. They are satisfying the aromaticity. If another compound is given, and it might not be furan, it might not be typhine, it might not be pyro, if they don't satisfy the 4 conditions, they are not aromatic. Okay. Assuming you are giving the first one here, and then the 2 double bonds are not there, it does not become furan again. Without the 2 double bonds, okay, it is an epoxide. It is no more a furan. So you treat it as such, and then say that it's not aromatic, and then you give reasons. The reasons, one of them will be that it's because the 2 double bonds are not there, the carbons in the ring will be what? sp3 hybridized, meaning the molecule will not be fully conjugated. So it is non-aromatic. Okay. And then if the 2 double bonds are not there, it will not obey Hackles rule. So you can say that it's what? Anti-aromatic.
Okay.
All right.
Thank you, Doc.
Now, the resonance structure showing the donation of the 2 electrons. We are saying that the pyro, the furan, or the typhine, they donate a lone pair into the ring to form parts, so that the pi electron system in the ring would satisfy Hackles rule. So this is how they do it. Okay. So if you take the oxygen, it donates these 2, 2 electrons form a bond. So it will push and form a double bond here. If you form a double bond here, 2 double bonds cannot, in an aromatic system, 2 double bonds cannot be adjacent to each other. So if you push these 2 lone pair of electrons here and form a double bond here, this particular one cannot be there. It will break onto this as minus here, okay? And then when that one also breaks here and form the double bond here, it seems that this one can also not stay. That one has to also break over here as a minus here. And when that one also break and form a double bond here, okay, then this particular one has to also break. So then it goes on and on and on. And that is what we call the resonant structures, or the canonical structures. Okay, so furan has this 1, 2, 3, 4, 5, typhine, and then pyro. This is how they end up donating the lone pair that makes them what? Aromatic. So we keep on talking about this, and it keeps on coming again. Satisfactory point for aromaticity. What are the things that makes a compound aromatic? And we say they are supposed to be cyclic or ring. They are supposed to be planar or flat, and then they should have what? 3 pairs of the localized pi electrons, meaning they should be fully conjugated, and then they should obey Hackles rule. Okay, and when they have satisfied these 4 conditions, then we say these are aromatic, and these aromatic compounds basically become very, very stable. So they do not undergo the typical addition reactions, electrophilic addition reactions, like we saw in alkenes and alkynes. Rather, they undergo electrophilic aromatic substitution reactions because of their high stability. Now, for any aromatic, like we saw in the benzene, for any aromatic proton, for heteroatom, we say the benzene, we said that the benzene protons, they absorb between what? 7 to what? We said 7 to what? 10 ppm. You've forgotten. I show you the proton NMR diagram of benzene protons and then carbon in benzene. And we said that the protons are always within the range of 7 to 10 ppm. Then the carbons are always within the range of what do you call it?
128 ppm.
128 or so, yeah. So that of the hydrogen of hetero aromatic compounds, the protons will appear in the NMR region between 6 to 9 ppm. Okay, 6 to 9 ppm. Now, pyro, furan, and thiophene exhibit basic properties. Okay, they exhibit basic properties. And so we need to look at the basicity of this pyro, furan, thiophene. And unlike the amines, which also contains nitrogen, the nitrogen atom in pyro share its non-bonding pair of electrons into the ring for aromaticity. In addition to contributing to these 2 electrons to the pi molecular orbital, the nitrogen in pyro shares 3 electrons in sigma bonds to 2 ring carbons and to a hydrogen atom. And as a result of that, all 5 of the bonding electrons of nitrogen are used in bonding. Pyro is therefore extremely weak base. So you see, basicity here is being defined by the availability of this pi electrons, okay, on the nitrogen. Now, unlike amines, that this pi electrons are available, and then that makes them more basic. In the case of the nitrogen in pyro, that lone pair has already been used in pushing to be part of the ring, to form part of the aromaticity. And so it does make them less basic, because the available lone pair of electrons are no more readily available. So if you are talking about basicity or the basic strength of a pyro compared to that of an amine, then the amines are stronger bases than the pyro. And that is the explanation I just gave. That is what is captured here. Sulfur is less electronegative atom, hence easily localizes the electron into the ring, like the pyro, and has a vacant d orbital that can be used in addition to the p orbitals in the delocalization, and so it's more stable than the other 2. Oxygen is the most electronegative heteroatom and has no vacant d orbital. Hence, furan has the smallest resonance energy. So all that we are doing now is that we are looking at the order of resonance energies, okay? So it means that furan is the least, followed by pyro, thiophene, and then benzene has the highest resonance energy. Try a question here. Which one is more basic? Explain. So you could see that the first one here is pyro, okay? But then the second one here is a cyclic amine. So it means you are comparing the basic strength of amine to a pyro. And we have already said it that the pyro, because the lone pair of electrons forms part of the aromatic molecular orbital structure, and so it makes the lone pair of electrons not readily available. So that makes them less basic compared to the amine, in which the lone pair of electron that will be on this nitrogen does not form part of any aromatic, because this is not aromatic. So the 2 lone pair of electrons are readily available, and that makes them more basic. So take note of that. Reactivity of furan, pyro, and thiophene. So here, the focus on the heterocyclic compounds is on furan, pyro, and thiophene, but there are a number of them. There are more examples, which at the latter part of the course, it will come out. And like I said, after this lecture, what it means is that we might only need one more meeting to finish this course. So I think this style is also not bad, whereby I could have combined the natural product 2 with this one, but now the focus has been on this one. We will make up with the natural product as well, and then you will be fine. Any question, please? All right. So now with the reactivity, how did they react? They are all aromatic, so definitely you expect that they will undergo electrophilic aromatic substitution reactions like benzene. So please, the benzene reactions that we know, the nitration, the sulfonation, the halogenation, the Friedel-Crafts alkylation, the Friedel-Crafts acylation, which we look at them when we're looking at the naphthalene, anthracene reactions. Please, this furan, pyro, and typhene also undergo similar electrophilic aromatic substitution reactions. In this case, the heteroatoms donate the non-bonded electrons into the pi cloud ring, making the heteroatoms relatively electron deficient and increasing the electron density on each carbon atom. For that matter, they are more reactive than benzene towards an electrophile. They are more reactive than benzene towards an electrophile. So in terms of reactivity, these three, the furan, the pyro, the typhene, are more reactive than what? Benzene. Now, the order of electrophilic substitution reaction is that the pyro, the pyro contains nitrogen. That one is more reactive than the furan, which contains oxygen. And that one is more reactive than the typhene, which contains sulfur. And then benzene is there. The reason to this trend is what is captured here. I will ask you in an exams. So please pay attention.
Okay, Doc.
And so furan is less reactive than pyro in electrophilic reaction because oxygen is greater electronegative atom than nitrogen. Hence, oxygen does not effectively donate its non-bonding electron into the ring, but then nitrogen does. The typhene has its non-bonded pi electron in a 3p orbital, which overlaps less effectively than the 2p orbitals of nitrogen or oxygen, which happens with the 2p orbitals of carbon. For that reason, the electron density is maintained in the vicinity of the sulfur and not on the carbon atoms. And so that makes it less reactive. So these are the reasons that support the trend that you can see. Now, let's look at the site of electrophilic aromatic substitution. If you have benzene and you are performing electrophilic substitution reaction, if there's no group on benzene, any of the carbon atoms, the substitution can take place, right? But then when there's a group on benzene, then that group has an influence as to where the incoming group should go. So you remember we said when there's an electron donating group on benzene, it will direct any incoming group to the auto and para position. So you form two products. The para product being the most stable, and so the major product. And if the group on benzene is an electron withdrawing group, they deactivate the benzene ring, and so they direct any incoming group to the meta position. So for the pyro, furan, typhene, we also need to know the site where the substitution will take place. And you can see the pyro, the one with the nitrogen here. We have C2 and C3. Okay, these are the two sites where substitution can take place. But then the most stable one is the C2. Okay, now when we say C2, we know how to number them. We number from the heteroatom. So nitrogen 1, so this one will be 2, 3, 4, 5. So the second and then the third carbon, that is where we have the most stable intermediate carbonium ion. And so that is where the substitution will take place. So electrophilic substitution occurs at C2. So if I give you a pyro and then I'm performing nitration, where should the nitro group go? It should go to carbon 2. 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 It So you see an example here. This is furan, and you are doing halogenation. That's you're adding bromine and Lewis acid. There should have been AlBr3 here. So the bromine that is coming should go to the carbon 2. Substitute the hydrogen on carbon 2. If the carbon 2 is blocked, then the next site will be the carbon 3. Okay, so look at this one. You see that the carbon 2 here are all blocked with a methyl group. So when you are doing the halogenation, then the next effective site where the substitution can take place is the C3, and that's where the bromine will go. So when all the C2 sites are occupied, substitution occurs at the C3. However, the C3 is also activated towards electrophilic attack, and therefore mixtures of products can be formed depending on the reaction condition. So the substrate and then the type of electrophile counts. Okay, they also count. So when you have a pyro and you are doing nitration at this temperature, you have the carbon 2 and then the carbon 3 having the nitro, but then the carbon 2 is more stable than the carbon 3. So that is that. The product that you form a mixture. There are specific reactions of furan, pyro, and thiophene, halogenation. So you can see if you look at thiophene here, the carbon 2s are all free. So if you do chlorination, one of the carbon 2s gets occupied, but then further or continuous chlorination will also mean that the other C2 here is also going to be chlorinated. So you can have only one of the C2s being chlorinated or both being chlorinated. So you can get a mixture of product. So the bromination gives predominantly 2-bromothiophenone by the action of N-bromosuccinamide, NBS, as you can see. In iodination, the same thing. So all the halogens, if you are doing halogenation, you should expect that the halogen will go to the carbon 2, and then that will be the product form. If you have a halogenated thiophene, then Grignard reagent, you react with magnesium in ether, that is Grignard formation. You form your Grignard reagent. Now, anytime you have Grignard reagent and you do carboxylation, then you are extending the carbon chain, so there will be COO, MgBr. Then in acid hydrolysis, you form carboxylic acid. So please know the trend. You are a chemist now. So when I give you thiophene, how do you form 2-bromothiophenone? When you have 2-bromothiophenone here and it reacts with magnesium in ether, how do you form your Grignard reagent? When you have your Grignard reagent and you do carboxylation and hydrolysis, how do you form your acid functional group? All these reactions are known to you from the introduction to organic chemistry to the general chemistry. These are already reactions. We have looked at them in different systems, but you need to apply them here. Nitration, we already know nitration. Nitric acid in acetic acid, or acetic anhydride, or nitric acid in sulfuric acid. What is important is that nitration always brings about a nitro group substitution. So with this one, you could see that there is no group on the C2. So you do the nitration and then the nitro comes here. But for the second one, the pyro here, you see that one of the C2s, the carbon 2s, this one is occupied by a meter, so you cannot have another group coming here. But the other one here is free. So if you are performing nitration, then a nitro group will come to this side, and then you get this product. For the Kraft acylation, for the Kraft alkylation, they are all the same as we know in the reactions of benzene. Okay, for the Kraft acylation, you need an acyl group like what is here, acetyl chloride, and then you need other Lewis acid, or you can use thin chloride. and then you introduce the acyl group. You are removing only the chlorine, and then the acyl group here is joined to the position 2 of the hetero group. So more examples, as you can see, just for your reference. I need not to go through all of them. More examples are here. When it is benzene, you can perform Friedel-Crafts acylation and introduce an acyl group. Okay, the benzene is less reactive than the thiophene, the furan, and then the pyrrole. So if you have a furan 2, you have an acyl group here, so you can undergo Friedel-Crafts acylation. If you have pyrrole here, Friedel-Crafts acylation are all possible. Sulfonation is also introducing SO3H, that's sulfonic. So that one, conc sulfuric acid, or you can also use SO3 in pyridine, or SO3 in H2SO4, and all you do is that you are introducing SO3H. These are all reactions that we are aware, but then we are applying them to what? Heterocyclic compounds. Heterocyclic compounds. So that is sulfonation. Then reduction reaction in heteroatoms. There's what we call the Birch reduction. Please take note of this name and read more on it. The Birch reduction of thiophene with sodium in liquid ammonia produces 2,3-dihydro and 2,5-dihydrothiophene molecule. So what it means is that, you see, there are two double bonds. The Birch reduction always reduces an unsaturated system toward a saturated system. So when you use your sodium in liquid ammonia, which is the reducing reagent, you can either reduce one of the double bonds or both. Okay, you can either reduce one or both. So take note of that. Then we have catalytic reduction to tetrahydrothiophene. That is when you want to reduce all the two at a go. So you have two double bonds and then hydrogen and a nickel. That is used. We call that one the Renyi catalyst. What it means that both double bonds get removed at the same time. The same thing if you are using furan, both double bonds get reduced. So all we are saying is that heterocyclic compounds can be catalytically reduced and is going to target the double bonds in the hetero system. Either one or both are removed depending on the condition and the temperature. The one in which both double bonds in the ring are being removed, you could see the temperature is what, 200 to 250, very high. But if you also have a furan, that one just about 50 degrees, and you are still able to perform the same task by reducing the furan catalytically to a cyclic ether, which is an epoxide. Then let's look at, because they are aromatic compounds, they have a ring. How do they react to cause an opening of the ring? How do they react? Under mild conditions, furan can be hydrolyzed into gamma dicarbonyl compounds. So acetic acid and sulfuric acid, you heat, and then it cleaves, and then you open up the ring. This side will form, depending on the nature of what the furan, you form this product here, which is a dicarbonyl compound. So at this stage, my advice is that it's all about you having time to read, because all that I'm showing you here is the same application of our previous knowledge, and then the reaction we saw under benzene that is being repeated here. Just that now we are doing these reactions not on benzene, but we are doing it on what? Some heteroatoms like thiophenes, like furan, like what do you call it? Pyrrole. So there's nothing different, at all.
But please, Doc.
Yes.
The ring opening is what I'm confused about. How does it occur? How does it get broken or open up?
That is an assignment for you to go and try your hands on. Provide the reaction mechanism for the above reaction. Okay.
Oh, okay.
Go and have a look at it.
All right, Doc, I'll do that.
Industrial scale preparation of thiophen. How to prepare thiophen, you see, involves the reaction between N-butane. We all know N-butane is an alkane, and then sulfur at a very high temperature, and then you form thiophen with the release of what? Hydrogen sulfide. Hydrogen sulfide is not friendly. So how to get rid of this gas is very important. But then this is a basic method that can be used to synthesize thiophen. What about yes?
Oh, Doc, that is in the reaction that you just showed. The one that you just showed, you said that this in after that is in the reaction, hydrogen sulfide will be released. But I think I saw only one sulfur atom. But still in the distance, but still there is sulfur in the distance in the ring. So this one. So
It's just about balancing of equation, okay? So it means that you will need maybe 2 moles of this.
Okay.
Okay, yeah, just balancing of equation. That's it.
Okay.
And so that of pyrrole is also there. That one you don't need butane and sulfur. That one you need what? Acetylene, and then formaldehyde, formalin. We all know formalin. So pyrrole is prepared from a reaction between acetylene and formaldehyde, and is treated with ammonia under pressure. So when formalin or formaldehyde react with acetylene, you form this intermediate, and this intermediate, when treated with ammonia under very high pressure, and you form your pyrrole. So this is also a straightforward preparation of industrial preparation of what? Pyrrole. Then the furan too, how do you prepare it? Over here, it's just prepared by the carbonylation of perfluoraldehyde. This is a type of an aldehyde which is not common, and then it is normally prepared from corn. Okay, so that is the aldehyde which is prepared from corn. First of all, you perform this acid hydrolysis under heat, and then you form a pentose sugar, and then you do the dehydration, and then you form this perfluoraldehyde as an intermediate, which you later have to oxidize it under steam to take away the aldehyde, and then you get your furan. So the 3 heterocyclic compounds, we are talking about them all this while at the industrial level, at the high industry level. This is how they can be prepared or synthesized.
So Doc. Hello, Doc.
Yes.
So that is in the furan does. So I think we said it is prepared from the corn cob. That is in the one that require Brodia.
Yes.
So you heat it.
You want to prepare some?
Yes, Doc.
Yeah, you get money. Prepare and go and sell.
Okay.
because I don't know what other processing that we take the avodia through. We just dispose of, them, but then they have other useful, in the industry. So all right. So general methods for preparing substituted 5-membered rings. This one is general. It could be you are preparing a derivative of typhine, or a derivative of what, furan, or a derivative of what, what do you call it, pyro. This is a general method that can be used, and the name is the Parnor synthesis. The Parnor synthesis is used to synthesize pyros, and it's also applied to the synthesis of typhine and furan as well, where there's ring closure of open chain gamma dicarbonyl compounds, which yield the substituted 5-membered ring when treated with amine derivatives. In the case of pyro, phosphorus pentoxide for furan, and phosphorus pentasulfide for typhine. So the last stage after you form you've done the ring closure, depending on whether it's furan or typhine or pyro, you then will use amine if it's pyro, or phosphorus pentoxide if it's furan, or phosphorus pentasulfide. So I think the next slide gives you the summary in an equation form. Okay, you need this dicarbonyl compound, and when you have this, then if it is about the derivatives of furan, then you need this one, P2O4. If it's about pyro, then you need what? This reagent or an amine. If it's about typhine, then this is it. So that is the general synthesis. Now that process we are saying is regarded as a dehydration of the intermediate double bond as the enol, or its nitrogen or sulfur equivalent. So this is just an extra information, and some typical examples is what you can see here. How a dicarbonyl ends up as a derivative of what? Either a furan, a pyro, or a typhine. These are specific examples as a guide. Please make use of this slide, because everything that you need is here. You don't have to bother yourself and go and read any textbook or worry yourself with any other thing. This and then the other materials I have shared with you, which also gives further information and knowledge.
Okay, Doc.
Now, structure of indo-benzofuran and benzotyphine. So here we are moving from just a single heteroatom or heterocyclic compounds to now the complex ones. Okay, the indo, the benzofuran, the benzotyphine. What it means is that when a benzene ring fused with furan, it's called benzofuran. When benzene fused with typhine, it's called benzotyphine. When benzene fused with what? Pyro, it's called what? Indo. Now, for such heterocyclic compounds that contain 5-membered aromatic ring fused with benzene ring, none of the heteroatom contributes its electron in the delocalization of the pi electron of the ring system. In naming them, you start from the heteroatom, and any substituent attached to the ring is located and named in alphabetical order. So still, you start with the heteroatom when numbering and naming this type of compounds. So there are some here, nomenclature. Naming start from the heteroatom, and any substituent attached to the ring is located and named in alphabetical order. So let's take the indole, which is a benzene fused with what? Pyro. Okay. And this is benzofuran, a benzene fused with what? Furan. Benzotyphene, a benzene ring fused with what? Typhene. Hold on. So you see the nomenclature here. The benzene fused with furan is called benzofuran, but then there's a substituent here. So if you want to number, we say that the two rings start from the hetero ring and then the heteroatom here. So you number 1, 2, 3, 4, 5, 6, 7. So you get to know all the substituent positions. Now the bromo is on the number 2. So you have 2 bromo benzofuran. If you look at this one, you see that there's bromo and then there's nitro. But you always number from the heteroatom, oxygen. So 1, 2, 3, 4, 5, 6, 7. So the bromine is on the second carbon, the nitro is on the fourth carbon. So 2 bromo, 4 nitro, benzofuran. Then look at this one, the benzotyphene. Of course, you number from here. So the sulfur is 1, this is 2, 3, 4, 5, 6, 7. So the methyl is on position 3, then the ethyl is on position 5. But alphabetically, ethyl comes before methyl. So it becomes 5 ethyl, 3 methyl, benzotyphene. You will see a number of these for you to name. And for some, I will give you the name for you to produce the structure. Please take note of this when you are preparing or revising.
All right, Doc.
Alternative naming. There's another way that you can also name it. So let's also look at some of them. And apart from what I've shared on this slide, the other materials I've given you, they give more examples. The alternative naming, they give more examples. So when you understand the basis from here, go and look at the other slide materials, okay? And then try to get more insight by looking at more examples. So the size of the heterocyclic ring can be labeled by letters, alphabet, A, B, C, etc. And it is always started from the atom numbered 1. So therefore, the side A is always between the number 1, atom numbered 1 and 2. The side B is always between the atom numbered 2 and 3, and so on and so forth. So what we are saying is that the alternative naming, you still give the number numbering, which starts from the heteroatom here, okay? You start from the heteroatom, and then you start from the heteroatom number 1, 2, 3, 4, 5. Then between number 1 and 2, the bond there, the side there is labeled as what? A. Between 2 and 3 is what? B. Between 3 and 4 is what? C. Between 4 and 5, okay, is D. But then what we have shown you here is that because there are no substituents, you can go anti-clockwise or clockwise. So 1, 2 is A, 2, 3 is B. So whether you go clockwise or anti-clockwise, it must end with the letters, okay? All right, so the alternative naming. The heterocyclic ring is the parent, and then the fused benzene ring is the benzo. So the benzo is used as what? A preface. So before you start the naming, because benzene is fused, just start with what? Benzo. When you finish writing the benzo, Then the hetero ring here, number it, like I've said, 1, 2, 3, 4, whatever. Then ask yourself, between 1 and 2 is A, 2 and 3 is B, 3 and 4 is C, okay? And then 4 and 5 is what? D. But then look at where the benzene is. If you go this way, it is going to be D. But we also have 1 and 2, that is A. 2 and 3, that is B. 3 and 4, that will be C. 4 and 5, that will be D. So if you look at the clockwise one, instead of D, you are going to get what? B. And of course, in alphabetical order, B comes before D. So IPAC say that go for the letter numbering. That is, closer. So the benzene ring is on the side B. So we say benzo B furan. The heteroatom is a furan. Now the B in the bracket here is the point of attachment of the benzene. The point of attachment of the benzene ring. And then the benzo here is telling you that it's benzene nucleus that is fused to the heteroatom. So this one will be benzo B thiophene, benzo B pyro. Okay. Now, though I have only introduced you to pyro, furan, and then thiophene, there are other heteroatoms which you need to be conversant with. This one is what? Pyridine. Okay, so pyridine is a heteroatom. Now you number from the nitrogen, and you have 2, 3, 4, 5, 6, 7, 8. So the side here is A, B, C, D, in that way. Then you can also go this way. Now, if you were to go anti-clockwise, then the benzene ring will be A, B, C, D, E. Far. But if you go clockwise, it will be A, B. So benzo B pyridine. Benzo B pyridine. Please, any question on this naming? Because we are getting to the latter part of the course, which I wouldn't want to continue, because now gradually I have to make sure that you properly assimilate whatever I give you. But like I told you, these courses you are doing in your final block, they are not that voluminous, okay? So that should be some good news for you. Any question, please?
Please, Doc, like I wanted to ask whether this hetero atom this thing, yeah, are we only limited to this three, the pyro and the typhine and the furan? Because right now you have introduced another one which, yeah,
so I've just shown you pyridine, okay?
Yeah.
And then the other slide, other materials I have given you talks about a number of other types, okay? We have the imidazole, we have the oxazole. In fact, there are a number of them. There are a lot. But at this level, you wouldn't want to be examining and then on all of them, but just to know the names, and then the common ones which we are going through, at least you understand. All right.
Okay, so okay.
Yes.
Hello, Doc.
Yes.
Doc, please, I'm asking, like, when the benzene is fusing with the three heterocyclic atoms, the nomenclature for naming is different from naming the rest of the heteroatom or the aromatic atoms, right? Because if you are counting, when yesterday, 3 days ago, we were learning the atrazine, the phenanthrene, and the rest. How we number it is we number it normally from the anti-clockwise. But right now, you just told us that we can do the clockwise base as far as the anti-clockwise.
Oh, please, it's not like you normally. What we normally say is that if you have naphthalene without any substituent group. Then the position 1 can be from this ring and it goes round, or it can be from the other ring and it also goes round. But when you start introducing substituent, then the substituent will let you know where to start from. Though you know the two position 1s already, but then the location of the substituent will say that, oh, you number from here, so that you give the list number to the substituent. So please, yes, there are specific numbering system for naphthalene, anthracene, phenanthrene. We have learned them already, and you follow it as it is. Here, the heteroatoms too, they are specific numbering, and I said that always start from the heteroatom in the ring. That's where the number 1 starts.
Yes, Doc.
Okay, and then that one to you go clockwise or anti-clockwise. If there's a substituent, that will determine whether you go clockwise or anti-clockwise. And we have even answered some questions here right now when we started this afternoon question. But we are saying that heterocyclic numbering, we have the 1, 2, 3, which can give you maybe the position of substituent. But now we are saying that when you fuse a benzene ring to a heteroatom, then we have what you call the benzofuran, benzopyrrole, benzotyphene. The benzo is because there's a benzene nucleus you have fused with the heteroatom. Now, after fusing the benzo or the benzene ring to the heteroatom, and we are now calling it benzo, we are saying that how do you name such? Okay, so the alternative naming is that after numbering the heteroatom, you see that the benzene is fused between 2 numbers. Now, if you check from the number 1 to 2, that side is giving A. 2 to 3, that side is giving B. 3 to 4 is giving C, in alphabetical order. So wherever the benzene is fused, when we start the numbering, the A, B, C, D, the alphabetical one, make sure too that you give the point of fusion the list from alphabet A, B, C. You give it the list where it is fused with the heteroatom, and that figure is put in the bracket. So you say benzo A, benzo B, furan, or benzo C, typhene, or benzo D, pyridine, depending on the side that the benzene ring had fused, the label that was there, the alphabetical number that was there. So treat each system and then the numbering as and when we get there. You don't say that, when I was dealing with phenanthrene, this is how I went about it. But this is not phenanthrene that we are looking at now. This is a different class of aromatic compound. So you learn how it should be numbered and then treated.
Thank you, Doc.
So we have looked at the aromaticity of furan, typhene, and then pyrrole. And I show you that they had some lone pair of electrons which forms part of the aromatic. They donate it to the ring, and then it makes them to satisfy the Hacker's rule. So now the benzofuran, the benzotyphene, and then the indole, are they aromatic? And the question is, if they are aromatic, do they qualify the 4 criteria for aromaticity? Yes. So they are aromatic because they are cyclic. That's the first condition. They are planar, the second condition. And they have 5 odd pairs of delocalized pi electrons. So if you look at this one.
Hello, Doc.
If you look at this one, can you see my arrow?
Yes, Doc.
So this one is benzo B pyrrole. Now, if you look at benzo B pyrrole, the benzene side, there are 3 pi bonds. And so that means that how many pi electrons? 6. Is that right?
Yes, Doc.
Good. Then when you come to the hetero ring, there's one double bond here, which is having 2 more electrons. So when you add it to the system, it makes what? 8, isn't it? Then the heteroatom, the nitrogen has a lone pair, which we say that it always donates that lone pair to be part of the ring system. So when you push these two to be part, then you're having what? 10, isn't it? So the total number of pi electrons here is 10. Does 10 form part of the Haeckel's rule of 2, 6, 10, 14, 18, 22? Does it form part? Yes. So that means that Indo, Indo, which is the same as benzo B pyro, is aromatic. It's aromatic. And over here, apart from the fact that it's aromatic, we are also showing how the pi bonds, delocalization goes through for you to get a different what? Canonical forms. So this shows that the indole is what? Aromatic. The benzofuran is aromatic. The benzotyphene is aromatic because the lone pair of electron on the heteroatom is pushed into the ring to form part of the pi delocalization electron system. So self-assessment questions. Provide IPAC names for the following. You want to try?
Yes, Doc. Let's try.
So let me give you some 5 minutes like we did for the other one. Let's try our hands on it, and we'll come back and discuss it.
Hello, Doc.
I said we're giving ourselves some time, 5 minutes. So you go through and then let's wait for the others and then we'll discuss. All right. I'm sure we've all gone through.
Yes, Doc.
All right. So, Frimpong, you want to pick up?
The first one.
Okay.
The pack name for the first one, I think, is 2,7-dibromo benzobifuran. And the second,
Come again.
2,7-dibromo benzobifuran.
Okay. Is that what the others are getting?
And the two.
The others, are you with us? I hope you are all with
Yes.
us.
Yes,
All right.
Yes, Doc.
So let's continue. The second one
is 2-bromo 4-nitro 6-methyl benzobifuran. 2-bromo 4-nitro 6-methyl benzobifuran.
Okay.
And the II for the third one is 5,7-diethyl 3-methyl benzobithiophene.
Come again.
7-diethyl 3-methyl benzobithiophene.
3, 5, 7.
No, it's 5,7.
Oh, okay.
5
7 diethyl.
3-methyl benzobithiophene.
All right. So
Hello, Doc.
yes.
Please, I also got for the last one, the III.
Mm-hmm.
I also got 2,4-diethyl 6 2,4-diethyl.
Okay.
6 meter benzobi.
Please, can I go on?
Yes. Go ahead.
2,4-diethyl 6-methyl benzobithiophene. That's what I got.
Okay, so what I think you drew our attention to is the numbering system, the one that is giving the list number to the subsequent.
Yes.
But you see, in the numbering system, you have to finish numbering the heterocyclic ring first. Okay. All right. I think I have to also cross check which one of them. I'll cross check and get back to you on that. Okay.
Okay, Doc.
Yeah.
Hello, Doc.
Most importantly, yes, the other materials I gave should be able to clarify which one is more appropriate. Because that material I gave, because of some of these things, it gives more detailed understanding as to how it should be. All right. So please, beyond this material, I think I shared some other too. Try and then look at that one as well. Any other person with any contribution? Yes, I'm here.
Hello, Doc. Doc, is it compulsory to bring the alphabet to in addition to the naming? Because you said the alphabet is an alternative to the first one. That's naming of the heteroatoms.
Yeah. So here the heteroatom has been fused to a what do you call it? A benzene, and so you see the parent name that they were giving. They say benzothiophene, benzofuran. So it means that has become part of the parent name. Okay. So now at what point is the benzene fused to the heteroatom? That is a B. Okay. And then the subsequent numbering too. Yeah. So it's very important.
Okay. Thank you, Doc.
So the second one said indole is an aromatic compound. State 3 criteria that can be used to support this. I think it's all about the 4 criteria for aromaticity, isn't it?
Yes, Doc.
Yes.
It
Very
is
good.
cyclic, it is planar, it's fully conjugated, it obey Hackers with those things. Okay.
Yes, good.
So now the reactions of the indole, reactions of the typhine, reactions of the furan, which I wouldn't want to. That is the last aspect I will want to leave. Okay. Is the last aspect I'm coming. Hold on. Yeah, what is left is with the reactions, and that is the last aspect I want to touch on under this course. So please, you have time and then
Hello,
have yes,
hello, Doc.
yes.
It is raining here, but I can hear you. Just about the naming of the benzofuran, the benzo fusing with the other is fulan, the pyro, and the terpene. The slide that you just showed, that you said that it is the last slide that we are about to go through. If you can show that one to me, I want clarification on that. The one that reaction on.
Oh, I think I've. Is it
No,
this one?
that one, the one that just passed. No, no, the other one.
Here?
No, yeah, this one, Doc. Thank you.
Hmm.
If you are looking at how it has been named, I think that they first of all named the heteroatom phase, the heterocyclic atom phase before the benzene. If what I'm telling, that's my opinion. Before looking at this, you've named from the where the heteroatom is together with the benzene that it has fused with. So,
So you are confirming that the numbering you should fully number the heteroatom before you go to the benzene ring.
Yes, Doc.
Yes. Yes, I think I agree with your point. Yes. All right. So we will be looking at electrophilic substitution reaction, and you see this same electrophilic substitution reaction is for all aromatic and heterocyclic compounds, and we have been looking at them under benzene. We'll be looking at them under different system. So that is the last aspect we'll be looking at, which I wouldn't take it today. I would reserve that one for any time that we will have a lecture on the aromatic, so that will end and close the docket on it, and then the focus will be on the natural product too. Yes, any question? Any question? So please, if you wouldn't mind, I will want us to end today's engagement, and maybe you have some few time left. Maybe you can use that one to do your personal revision and then solve some of the questions, self-assessment questions, with the remaining time. Use it to engage and then look at some of my review tutorial questions as well. And class, can we reschedule this morning's class, which we missed because I had to teach the cohort 3. can we then go back to our Wednesday, Thursday evening classes? Can we go back this coming week? Can we do the same before the weekend?
Yes, Doc. We can. Yeah.
Right. So to me
That's a
that
good day.
Wednesday 6 to 8, Thursday 6 to 8, we will do it again. And in fact, if we do that, what it means is that we, for the 2 courses we have online, we are likely to finish ahead of time. Okay. Then maybe if we are to engage again, it can be maybe questions and answers. I will use it like a tutorial so that I can assist you, and then we can use the remaining time that we'll be getting in the subsequent weeks to solve questions to prepare you for your quiz and then your final exams. I hope that will be fine.
Yes, Doc.
Dog,
Very,
I'm
very
also
good.
dog. Hello, dog.
Yes.
I'm also suggesting that if
I'm listening.
we're able to finish on time, we should also get towards the time to go through the model given to us. So if we are able to finish this one on time, we should also veer into the practical aspect so that one too can give us more explanation to it. That's my
okay. Okay. So I will probably be like give you some pre-practical briefing before you go for your practicals. Yeah, that can be done. But then I can only do that for the one I'm coordinating. That's the Chem 319, the organic practical.
Yes, sir.
All right. Please, any other concern? Any other concern?
yes.
Please, Doc, I think that's all. So we can leave.
All right. So we'll be any other thing will be engaging on our platform. And gosh, lest I forgot. I keep on saying remind me because like someone wanted to be my TA from today going. The workload is really piling up, and then maybe very soon I'm going old. I have to start training some of you to take over.
Sir, I'm here. I'm still here. The TA
Yeah,
I'm
so
still available.
yes, so I will have to start that particular project. I need to train at least 1 or 2 of you to take over some of the work. So I need to pull together your natural products 2 slides that I have, and so I'll remind me to share them on your page, because our next
Okay.
meeting we should touch on that one. It's more of reading though, but we need to touch on and see how that one also goes. Thank you very much and have a nice day.
Thank you very much, Doc.
You too, Doc.
Bye.
Thank you very much.